It is a cold, moonless night. Mist hangs low, thick and heavy, clinging to the air like a living thing. As you step off the curb, the fog swallows everything at once, the sound of the engine, the glare of the headlights, the warning you never hear. You see the car too late. There is only time to brace for impact. And then, out of nowhere, an elderly stranger appears. A sudden shove, a violent force. You stumble backward, thrown clear of the road. The stranger is not so lucky. The car strikes them instead. They hit the tarmac hard. And there, in the cold and mist, their life ends, so that yours can continue. Later that night, a police officer approaches you quietly. In their hand is an envelope, recovered from the pocket of the deceased. It is addressed to you, your name, your handwriting, with trembling hands. You open it. Inside is a single slip of paper. 2 words, hastily scribbled: study physics. Whoever wrote that note saved your life at the cost of their own. And so, it feels only right that you follow their advice. Years pass, then decades. You become a physicist, a celebrated professor. Your specialty, Albert Einstein's theories of relativity. All your life, you carry a quiet suspicion, a hunch that time travel is not impossible, merely misunderstood. And one day, impossibly, you crack it. The world's first time machine hums to life before you. Only then does the realization strike. You now possess the power to go anywhere, any place, any time. And yet, you know exactly where you must go. You remove the letter you have kept framed on your wall for all these years, slip it back into its original envelope, place it carefully into your pocket. You step into the machine. You set the coordinates. A cold, moonless, mist-filled night. You arrive just in time to push your younger self out of the path of the onrushing car. You die on the roadside. Simple enough. But time travel stories are never simple, not once you scratch beneath the surface. Because now the questions begin. First, who wrote the letter? You only ever received it, and then carried it back in time to give it to yourself. The letter has no origin. It exists without a creator, trapped in a closed loop. This is the bootstrap paradox. Second, do these loops repeat forever? You save your younger self. Who grows up to save their younger self? Who grows up to do the same? A relentless cycle of living and dying. But the letter doesn't reset. Does it grow older, more worn, more fragile with every pass through time? This is the restoration paradox. Third, whose idea was it to study physics in the first place? The thought appears from nowhere. A decision without an origin. A cause without a cause. This is the ex nihilo paradox. And then comes the most unsettling implication of all. If events unfold this way, you never truly had a choice. You were always going to invent the time machine. You were always going to step into it. You were always going to save yourself. If you didn't, you would have died as a teenager. Something in your future was fixed from the very beginning. This is the predestination paradox. And finally, the darkest question. What if you change your mind? What if, upon arriving, you hesitate? What if you let the car hit your younger self? You can't. Because if your younger self dies, you never grow up to be there in the first place. Even inaction becomes impossible. This is the auto-infanticide paradox. Suddenly, the story is no longer simple at all. Welcome to the strange, unsettling, and beautiful world of time travel. Of course, you might say that time travel is impossible, that we cannot simply visit yesterday or race headlong into the distant future. And yet, it is not quite that simple. Despite its overwhelming impracticalities, physics allows slivers of possibility, tiny cracks at the edge of our understanding, temporal loopholes just beyond our reach. So the real question emerges. If time travel were possible, how would we actually do it? To begin answering that, we must first understand what time itself truly is. In 2021, a researcher at the University of Portsmouth calculated that the observable universe contains roughly 6 times 10 to the power of 80 bits of information, a 6 followed by 80 zeros. Information is not abstract. It is physical. It is fundamental. And understanding time may require understanding information itself. But long before equations and data, humans have searched for metaphors. Jack Finney, one of the great writers of time travel fiction, compared time to a river. Imagine drifting along a humid jungle river, carried effortlessly by the current. You do not paddle, you simply move. The past lies upstream, the future downstream. We cannot turn around. We cannot slow the flow, and we certainly cannot paddle back. But ask yourself this: what happens to the parts of the river you've already passed? Do they vanish? Of course not. The river upstream still exists, even if you are no longer there to see it. And yet, we often think of time differently, as though yesterday has disappeared, as though tomorrow does not exist until it arrives. That would be like believing the river only forms where you stand. So where would new time come from? Over the years, physics has revealed something extraordinary. Time is not flowing into existence moment by moment. It already exists, all of it, from the source near the Big Bang to its distant estuary at the end of the universe. Past, present, and future coexist. Your ancestors are still there. Upstream, your descendants already exist. Downstream, philosophers call this view eternalism. Physicists know it as the block universe, a direct consequence of Einstein's theory of relativity. In this picture, the universe is not a moving moment. It is a four-dimensional structure, where time is as real and fixed as space. And if that is true, then perhaps time travel is not about creating something impossible. Perhaps it is about learning how to move within something that already exists. And that is where the real journey begins. In 1905, Albert Einstein published the special theory of relativity, and with it, he quietly dismantled one of the most deeply ingrained assumptions in human thought, the idea of absolute time. In Isaac Newton's universe, time was universal. A single cosmic clock ticked forward identically for everyone. Everywhere, events happened in a fixed order, and the past, present, and future were the same for all observers. Einstein showed that this picture was wrong. There is no universal clock. Time itself depends on how you move through space. Two observers, traveling differently, can disagree about the order of events. One might see event A happen before event B. Another might see B occur before A. And, astonishingly, both are correct. An event in your past can exist in someone else's future. This alone shatters the idea that yesterday simply disappears. How could it, when the events it contains may still lie ahead for someone else? Special relativity also revealed something even more radical. Space and time are not separate things at all. In 1908, the mathematician Hermann Minkowski completed Einstein's vision by formally uniting them. He showed that the 3 dimensions of space and the single dimension of time are woven together into a single 4-dimensional fabric. He called it spacetime. Moving through space affects how you experience time, because motion happens within this unified structure. The block universe is not built from space plus time. It is built from space-time itself. But how do we know this isn't just elegant mathematics? The proof came from Einstein's next great leap. In 1915, he presented the general theory of relativity, a theory that did more than describe motion. It redefined gravity itself. The road to this insight began decades earlier. In the 1,840 seconds, astronomers noticed something strange about the planet Uranus. Its orbit deviated slightly from predictions made using Newton's laws. The French astronomer Urbain Le Verrier spent months reworking the equations. Was Newton wrong? Not yet. Le Verrier proposed that an unseen planet farther out was tugging on Uranus. If such a planet existed, Newtonian gravity would be vindicated. In 1846, Neptune was discovered, exactly where Leverrier predicted. A triumph, but hidden within this success was the seed of Newtonian gravity's downfall. Planets do not follow perfect circular paths. They trace slowly rotating ellipses, with the sun offset from the center. Newton's equations explained this motion beautifully for every planet except one, Mercury. In 1859, Leverrier realized that Mercury's orbit drifted in a way Newtonian gravity could not fully explain. The search began for another unseen planet. None was ever found. The solution arrived instead from Einstein. On November 18th, Einstein wrote to the mathematician David Hilbert, "Today I am presenting a paper in which I derive from general relativity the perihelion motion of Mercury." Discovered by Leverrier. No gravitational theory had achieved this until now. To understand what Einstein had done, imagine space-time as the surface of a trampoline. Place a heavy object in the center, and the surface sags. That sag is what physicists call a gravity well. The sun does not pull Mercury through some invisible force. Instead, the sun curves space-time around itself. Mercury, moving deep within that curved geometry, follows the straightest possible path, which appears to us as a slowly rotating orbit. Gravity is not a pull. It is the consequence of curved space-time. For most planets, the curvature is gentle enough that Newton's equations work as an approximation. Only in Mercury's extreme gravitational environment does the illusion break down. Since then, this idea has been tested relentlessly. Solar eclipses bending starlight, orbiting pulsars, swirling black holes, rippling gravitational waves. In every case, space-time behaves exactly as Einstein predicted. Our entire cosmos past, present, and future is a four-dimensional structure that simply exists. A hypothetical being observing the universe from the outside would see yesterday, today, and tomorrow all laid out at once. So where did this space-time come from? Like everything else, scientists believe it emerged with the Big Bang. Not just matter, not just energy, but all of space and all of time. The past, present, and future are not being created moment by moment. They already exist, fully embedded within space-time. This is why people separated by centuries can coexist in the block universe, just as people separated by kilometers coexist in space. Any object within this universe can be assigned 4 coordinates, 3 to say where it is, and 1 to say when it is. Even a stationary object traces a path through time, second by second. Today becomes tomorrow. If you plot all those positions together, you get a line through space-time, a world line. You are nothing more than a tangled bundle of world lines. Particles entering, particles leaving. A knot in space-time that forms, persists, and eventually unravels. Every action you will ever take, what you eat, who you love, the paths you follow is mapped along those lines. You cannot deviate from them any more than a train can leave its tracks. The block universe is like a book already written. The beginning, middle, and end are fixed. A character on page 150 may not know how their story ends, but the ending exists nonetheless. And this is why the time traveler in our opening story had no choice. They had to invent the time machine, because an older version of themselves already existed earlier in the book. Their world line looped back and intersected itself. But is such a thing truly possible? If over then is no different from over there, does that mean the door to time travel is actually open far across the universe? A supermassive black hole grips an entire galaxy in its grasp. Its gravity shreds stars. Its magnetic fields hurl jets of matter into intergalactic space. Among the debris is a single subatomic particle, a proton. It is accelerated to nearly the speed of light. It carries 100 quintillion times the energy of a visible photon. After traveling more than 1 billion light-years, it strikes Earth's atmosphere, The collision releases 21 million times the energy produced inside the Large Hadron Collider at CERN. Astronomers gave it a fitting name, the "Oh my God" particle, and in its existence lies a clue, a reminder that the universe already allows objects to experience time in profoundly different ways. The deeper we look, the more fragile our assumptions about time become, and the stranger the question grows, not whether time travel is forbidden, but why the universe allows it at all. An ultra-high energy cosmic ray is not just a scientific curiosity, it is a warning. It reminds us that Earth exists inside a celestial shooting gallery, constantly bombarded by particles accelerated to unimaginable energies. When a cosmic ray like this one slams into our atmosphere, the collision is so violent that it triggers an invisible fireworks display. Subatomic particles erupt outward pions, muons, neutrinos cascading through the sky in vast particle showers that spread for kilometers before quietly reaching the ground. Cosmic rays are so common that they deliver to your body an annual dose of radiation equivalent to 3 chest X-rays. Most pass unnoticed. Some leave subtle traces, and for one Italian physicist, they became an obsession. His name was Bruno Rossi. Rossi would become one of the pioneers of high-energy astrophysics, and through his work, he provided some of the earliest experimental evidence that time travel to the future is not science fiction at all. It is a routine consequence of physics. Picture Rossi behind the wheel of an aging bus, winding along what was then the highest road in the world. Pine trees thin out, snow-capped peaks loom closer, and the air grows sharper with altitude. After driving more than 1,000 miles from Chicago, he reaches his destination, Echo Lake, perched high in the Mount Evans wilderness of Colorado, nearly 300 meters above sea level. Here, above the dense lower atmosphere, Rossi sets up his experiment. Cosmic rays striking the upper atmosphere produce muons, unstable subatomic particles that rain down toward Earth at extraordinary speeds. Muons decay quickly. Physicists define their half-life as the time it takes for half of a group to disappear. For muons, that time is just 1/56 millionths of a second. At first glance, this creates a puzzle. Muons are created many kilometers above the ground, even traveling at more than 98% the speed of light. They should experience over 15 half-lives before reaching Echo Lake. Each half-life wipes out half of the remaining population. By the time they arrive, only 0.1% should survive. And yet, Rossi detected far more than that. The numbers didn't add up unless something extraordinary was happening. The solution was both simple and profound. The muons were time-traveling. Einstein's special theory of relativity tells us that everything moving through space-time has a fixed budget, equal to the speed of light. The more of that budget you spend moving through space, the less remains for moving through time. The muons are racing through space at near light speed. As a result, time passes more slowly for them than it does for Rossi. From their perspective, fewer half-lives have elapsed. They simply haven't had enough time to decay. This phenomenon is known as relativistic time dilation. Once Rossi accounted for it, the measurements fell perfectly into place. The experiment didn't just confirm Einstein's theory, it demonstrated, unmistakably, that objects can move into the future faster than the rest of the universe. But does this really count as time travel? Imagine you are the muon. Instead of traveling from the upper atmosphere to Echo Lake, you embark on a vast loop around the universe at 98% the speed of light, eventually returning home. From your perspective, perhaps 25 years pass, but back on Earth, those who stayed behind were moving more slowly through space and therefore faster through time. When you return, 125 years have elapsed on Earth. You have leapt a full century into the future. This is not speculation. It is a direct, measurable consequence of relativity. Such journeys could even scramble generational relationships. A theme explored poignantly in Ken Liu's short story, Memories of My Mother. Time travel to the future then is not forbidden. It is merely difficult. The challenge lies in speed. As Einstein's famous equation E equals mc squared reveals, energy and mass are interchangeable. The faster you move, the more energy you carry, and to an outside observer, the more massive you become. A human traveling at 99% the speed of light would appear to weigh nearly 2 tons, roughly the mass of a rhinoceros. Accelerating someone to that speed would require as much energy as all of humanity consumes over 3 months. Unsurprisingly, this remains far beyond our capabilities. And yet, time dilation is not confined to thought experiments or cosmic particles. It affects real people. Consider Mark and Scott Kelly, identical twins and former NASA astronauts. While Scott spent nearly a year aboard the International Space Station, moving faster through space than his brother on Earth, Mark remained behind. When Scott returned, he was by a tiny but measurable amount younger than his twin. The difference was only milliseconds, but the implication was enormous. Time had not flowed equally for both of them. The universe had allowed one human to step, however slightly, into the future. And if that is possible, then the deeper question remains, not whether time travel exists, but how far its strange permissions truly extend. Mark Kelly was born 6 minutes before his twin brother Scott. At birth, Mark was the older one, but life had other plans. Scott would go on to spend far more time off Earth, accumulating 520 days in space, compared to Mark's 54 days. During those extra months, Scott was hurtling through space-time faster than his brother, orbiting Earth at tremendous speed, spending more of his space-time budget on motion and less on time itself. The result is subtle but real. More time has passed for Mark than for Scott. Mark may have entered the world 6 minutes earlier, but today he is 6 minutes and 5 milliseconds older than his twin. A tiny difference, imperceptibly, to human senses, yet undeniable. And had Scott been travelling as fast as a muon near the speed of light, that age gap would have stretched to nearly 6.5 years, despite the two being born on the same day. Time, it seems, is negotiable. And as if motion through space weren't enough, physics offers a second, entirely different way to travel into the future. To understand it, imagine a clock, but not one that hangs on a wall. This clock is made of 2 mirrors facing each other. A beam of light bounces back and forth between them, and every time the light strikes a mirror, the clock ticks. It is one of the simplest and most precise clocks imaginable. Now imagine you build 2 identical copies of this clock. You leave one safely behind, far from any strong gravity. The other, you lower deep into a gravitational well, a region where space-time is more strongly curved. Inside that well, space-time itself is warped. The light bouncing between the mirrors no longer travels in a straight line. It follows a longer, curved path. As a result, the clock ticks more slowly. Bring the 2 clocks back together, and you will find that less time has passed on the one that ventured into the gravitational well. This is gravitational time dilation. And just like motion-based time dilation, it can be used to travel into the future. Spend time deep inside a strong gravity well, then return to Earth, and you will find that more time has passed here than for you. You can leap forward decades, even centuries, provided the gravity well is deep enough. Earth's gravity is far too weak for dramatic effects, but supermassive black holes are not. This very idea formed the backbone of the film Interstellar, guided by physicist Kip Thorne, where astronauts skim the edge of a black hole and return to find decades have passed on Earth. Yet gravitational time dilation is not confined to science fiction. When Bruno Rossi drove his bus up the winding road to Mount Evans, he was climbing out of Earth's gravity well. High in the mountains, space-time is fractionally less curved than at sea level. Rossi aged slightly faster at Echo Lake than he did back down the mountain. The effect is unimaginably small for humans, but not for machines. Atomic clocks are so precise that they lose or gain less than 1 second over 15 billion years. Place 2 synchronized atomic clocks on shelves at different heights in a laboratory, and they will slowly drift out of sync. In 2022, physicists measured gravitational time dilation using clocks placed just 1 millimeter apart. And this isn't just academic. You rely on time dilation every day. The Global Positioning System GPS works only because physicists correct for both kinds of time dilation. GPS satellites move rapidly through space and sit higher in Earth's gravity well. Their onboard atomic clocks tick at a different rate than clocks on the ground. Without constant relativistic corrections, GPS errors would accumulate by kilometers per day. These experiments leave no doubt. Time travel to the future is real. It is established, verified, and routinely accounted for in modern technology. But what about the other direction? What about traveling into the past? The year is 2011. Barack Obama is president. Prince William and Kate Middleton are newly married. NASA's iconic space shuttle lands for the final time. Then, in September, physicists make a shocking announcement. They appear to have observed neutrinos traveling faster than the speed of light. If true, it would shatter one of the most sacred principles in physics and potentially open the door to backward time travel. The claim comes from the Opera experiment. Buried deep beneath Italy's Gran Sasso mountain, neutrinos were fired from CERN, near Geneva, through 730 kilometers of solid Earth to the detector. At the speed of light, the journey should take 4 milliseconds. But the neutrinos seemed to arrive 16 nanoseconds early. They appeared to be breaking the universe's speed limit. Einstein's special relativity is unambiguous. The faster you move, the heavier you become. The heavier you become, the more energy is required to accelerate further. Eventually, the energy required becomes infinite. That barrier is the speed of light. Light, which has no mass, can reach it. Anything with mass cannot, let alone exceed it. And indeed, within a year, the mystery unraveled. The equipment was faulty. A loose cable had skewed the measurements. The neutrinos were not superluminal after all. Relativity stood firm. The universe, it seems, allows us to race forward through time but draws a hard line against going back. Or does it? That question still lingers, waiting in the shadows of physics, daring us to push just a little further upstream. The initial finding caused such upheaval because traveling faster than light would allow travel backward in time. And the reason why leads us back nearly a century, to a young Dutch physicist whose work quietly cracked open one of the most unsettling possibilities in modern science. In 1937, Willem Jacob van Stockum published a paper with a title so unremarkable it gave no hint of what lay inside. The gravitational field of a distribution of particles rotating about an axis of symmetry. Dry, technical, easily overlooked. Yet hidden within those equations was something extraordinary. Van Stockum showed that Einstein's general theory of relativity allows closed time-like curves, paths through spacetime, that loop back on themselves. Normally, a world line stretches cleanly from past to future, but a closed time-like curve bends that line until it reconnects with an earlier point. Follow such a path, and a traveler could, at least mathematically, return to the moment of their birth, or step into the road to save their younger self from an oncoming car. Van Stockum had demonstrated something profound. There is nothing in Einstein's equations that outright forbids backward time travel. At first glance, however, there is a catch. To bend your future world line into a loop, it seems you must travel faster than light, escaping what physicists call your light cone. Your world line is the single path you actually take through the block universe. Your light cone, by contrast, represents all the paths you could possibly take without violating the cosmic speed limit. Imagine you are standing still in space. Your world line moves straight upward through time. 1 second from now, you can be no more than 300. 0.000 kilometers away, the distance light can travel in that time. 2 seconds from now. Liu Bei. 0.000 kilometers. 3 seconds. Zhou Bai. 0.000 kilometers. As time advances, the region of space-time you can reach expands outward, forming a cone. The edges of that cone are traced by beams of light. Unless you can outrun light itself, you are forever confined within it. And that seems to seal the case. To loop backward and intersect your own past, you would have to leave your light cone, which appears impossible without exceeding the speed of light. But relativity has another trick. There is a second way to reach the past, not by escaping your light cone, but by tilting it. If space-time is curved strongly enough, your light cone can lean backward, allowing a closed time-like curve to remain inside it at every step. You never outrun light. You simply ride the geometry of space-time itself. In 1974, American physicist Frank Tipler explored exactly this scenario. He studied a theoretical object now known as the Tipler cylinder, a massive cylinder containing at least 10 times the mass of the Sun. Rotating along its length, Tipler showed that if this cylinder rotated fast enough, space-time around it would be dragged into a violent twist. A traveler following a precise spiral path around the cylinder would find their light cone gradually tipping backward. Because a world line must always lie inside the light cone, the traveler would be carried inexorably into the past. Visit the cylinder, loop around it, return to Earth. You arrived before you left. On paper, it worked, but reality was less accommodating. To make the mathematics tractable, Tipler had to assume the cylinder was infinitely long. He could not prove that a finite one would suffice. Worse still, the cylinder would need to rotate billions of times per minute to warp space-time enough. Hardly a practical time machine. Then, in the 1990 seconds, Stephen Hawking added another formidable obstacle. He argued that a non-infinite Tipler cylinder would also require enormous quantities of negative energy, a substance that behaves nothing like ordinary matter. And this is where quantum mechanics enters the story. Alongside relativity, quantum theory is one of the great pillars of modern physics. Unlike classical physics, it allows for strange effects that seem to flirt with the impossible. In certain quantum systems, tiny amounts of negative energy density can briefly exist, but tiny is doing a lot of work here. The amounts permitted by quantum mechanics are so minuscule, so fleeting, that scaling them up to the levels required for a working time machine appears utterly implausible. Hawking argued that as soon as space-time began to curve enough to allow closed time-like curves, quantum effects would explode in response, destroying the configuration before time travel could occur. He called this idea the chronology protection conjecture, nature's way of preventing paradoxes. Time, it seems, may allow shortcuts into the future, but when it comes to the past, the universe fights back. And yet, the door is not fully closed. Because every one of these ideas, Van Stockham's curves, Tipler's cylinder, Hawking's objections, emerges directly from the equations that describe our universe. The mathematics does not forbid time travel outright. It merely buries it behind conditions so extreme that they may never be realized. For now, which leaves us with an unsettling conclusion. If the laws of physics permit backward time travel in principle, even if they conspire to prevent it in practice, then the paradoxes we explored at the beginning are not just storytelling devices. They are warning signs, signals from the edge of physics itself, hinting that time is far stranger, more fragile, and more deeply woven into the fabric of reality than our everyday experience would ever suggest. And that raises the question that still haunts physicists today. Is time travel truly impossible? Or have we simply not yet learned how to bend the universe far enough to make it happen? Einstein's general theory of relativity governs the grand structure of space-time. But when we descend into the subatomic world, quantum physics takes over. And there, the universe behaves very differently. According to quantum theory, even empty space is never truly empty. The vacuum seethes with activity. Pairs of so-called virtual particles constantly flicker into existence and vanish again, borrowing energy from the vacuum itself. For a fleeting moment, the local energy of space dips below zero, much like a bank account slipping into overdraft. But just as the bank always demands repayment, the universe insists that this borrowed energy be returned. Negative energy does exist, but only in tiny regions of space, and only for vanishingly short periods of time. This limitation has profound consequences. While closed time-like curves may exist at the subatomic level, creating a stable time loop large enough for a human being to traverse, large enough to revisit the past, appears to be an entirely different challenge. Yet there may be another way. A way to cheat the seemingly sacred rule that the speed of light is the ultimate cosmic speed limit. A wormhole. In 1985, the celebrated astronomer, author, and television presenter Carl Sagan published his novel Contact. In the story, an advanced alien civilization sends humanity the blueprints for a device capable of transporting a single person across the vast gulf of space to the star Vega, 25 light-years away. But Sagan faced a problem. Nothing can travel faster than light. A journey to Vega should take decades. He needed a way to get his heroine there quickly without breaking the laws of physics. So Sagan did what any good scientist does when stuck. He called a friend. That friend was Kip Thorne. Sagan overnighted the manuscript, and Thorne read it the next morning while driving to his daughter's graduation. Somewhere between the pages and the calculations scribbled in his head, the solution appeared. What Sagan needed was a wormhole. Imagine space-time as a flat sheet of paper. Earth lies on one end. Vega lies far away on the other. Traveling across the paper takes time. But if space-time can curve, and Einstein showed that it can, you could fold the paper so that Earth and Vega touch. Step across the fold, and you arrive instantly. From the outside, it looks as though you have traveled faster than light. But you haven't. You never broke the speed limit. You simply took a shortcut through space-time itself. And if a wormhole can connect distant points in space, it can also connect different moments in time. Suppose a wormhole already exists between Earth and Vega. Now attach the Earth-side mouth of the wormhole to a rocket and accelerate it on a long journey at near light speed. Because that mouth spends more of its space-time budget on motion. Less time passes for it than for the stationary Vega mouth. When the traveling mouth returns, the two ends of the wormhole are now out of sync in time. Step into the wormhole, and you emerge in the past. At first, this sends you backward in time, but only to Vega's history, not Earth's. Yet even that limitation can be overcome. Arrange the geometry correctly, and ensure that the time difference between the wormhole mouths exceeds the time it takes to travel back to Earth, the conventional way, and you arrive home before you ever entered the wormhole. At least, in theory. In practice, things become complicated very quickly. Thorne realized that anything passing through a wormhole would exert a gravitational pull on its structure, threatening to make it collapse. To keep a wormhole open, something must prop it apart. Once again, negative energy appears as a possible solution. Other ideas have also been explored, from intense magnetic fields to exotic quantum effects. And wormholes are not the only theoretical route. In 1985, Richard Gott and William Hiscock solved Einstein's equations for cosmic strings, hypothetical. Ultra-dense defects in spacetime formed in the early universe. 6 years later, Gott realized something remarkable. Follow the correct path around a pair of rapidly moving cosmic strings, and spacetime itself could twist enough to tilt your light cone backward. Once again, the past becomes accessible without ever exceeding the speed of light. Quantum entanglement offers another tantalizing hint. Entangled particles remain linked no matter how far apart they are. Change one, and the other responds instantly, as though information has traveled faster than light. Yet despite appearances, Physicists have shown that usable information cannot be transmitted superluminally this way. Still, the implication remains unsettling. There appear to be multiple paths, at least mathematically, that allow backward time travel without violating relativity. But if time travel to the past were possible, what about the paradoxes here? Quantum theory may offer an escape. Imagine this. Cold metal handcuffs bite into your wrists. Sweat runs down your face as you stare at the table in front of you. On it sits a glass vial filled with lethal gas. Next to a hammer mounted on a robotic arm. The arm is connected to a machine measuring subatomic particles. Each particle can be measured in one of two states, A or B. The odds are 50-50. If the outcome is A, nothing happens. If it is B, the hammer falls. The vial shatters, and you die. The machine will make 100 measurements. Your odds of survival are roughly 1 in a million trillion. The first measurement clicks. A. You exhale. The second. A. The 10th. A. Hope creeps in. Against all reason. After 99 consecutive A's, you are dizzy with disbelief. It all comes down to the final measurement. The machine clicks. A. You survive. Unbeknownst to you, your impossible escape has just provided evidence for one of the most radical ideas in physics, the many worlds interpretation of quantum mechanics. This is a human version of Schrödinger's cat. In quantum theory, before measurement, particles do not exist in a single state, but in a superposition of all possible states at once. The vial is both broken and unbroken. You are both alive and dead. So what resolves this ambiguity? According to the many worlds interpretation proposed by Hugh Everett III, nothing collapses. Instead, the universe splits. Every possible outcome occurs, each in its own branching reality. Outcome A happens in one universe. Outcome B happens in another. Reality fractures continuously, branching like a tree. The great river of time divides into countless streams. In some, you were never born. In others, you are president of Earth. And crucially, this framework offers a way out of time travel paradoxes. If you travel back in time and change something, you do not overwrite your own history. You simply create a new branch. The paradox dissolves. The universe accommodates every outcome by multiplying itself. Time travel does not break reality. It divides it. And that brings us to the edge of modern physics, where relativity, quantum mechanics, and philosophy collide. Time may not be a single, immutable arrow. It may be a vast, branching structure, one where the past still exists. The future already unfolds, and every choice echoes across countless unseen worlds. The question is no longer whether time travel is allowed by the laws of physics. The question is whether the universe is willing to pay the price. If this interpretation is correct, then performing 100 measurements with the poison and hammer machine would not result in a single outcome, but 100 separate branches of reality. In 99 of them, you die. In just one, you survive. As the lone surviving version of yourself, you marvel at your extraordinary luck. But that luck is an illusion. Across the multiverse, 99 other copies of you met their end. Some died after the very first measurement. Others endured almost the entire ordeal, only to perish on the final test. You alone remain. Not because the odds favored you, but because there is always at least one branch in which you survive. This unsettling idea is known as the quantum immortality experiment. No matter how many times the machine runs, there will always be a version of you that stubbornly refuses to die. In a strange sense, it is a game of Russian roulette that you can never lose, because the only version of you that remains conscious is the one that keeps surviving. Physicists do not know whether the many worlds interpretation of quantum mechanics is truly correct, but if it is, it offers a powerful way to resolve some of the most infamous paradoxes associated with time travel to the past. Consider the most famous of them all, the grandfather paradox. You travel back in time and murder your grandfather as a child. If he never grows up, he never meets your grandmother. If your mother is never born, neither are you. And if you were never born, how could you have traveled back in time to commit the act in the first place for decades? Writers, philosophers, and scientists have wrestled with this logical knot. Stephen Hawking proposed one solution he called the chronology protection conjecture. According to this idea, backward time travel is simply impossible. The universe itself conspires to prevent it, enforcing cause and effect as an unbreakable law. Another proposal came from Igor Novikov, whose self-consistency principle allows time travel to the past but forbids any changes to history. You may revisit earlier pages of the block universe, but you cannot rewrite them. Attempt to kill your younger self, and something will always intervene. The gun jams. You slip. They sneeze at the exact wrong moment. No matter what you try, you will fail. History remains intact, but this solution raises troubling questions of its own. Does it mean the future is fixed? Is free will an illusion? And worse still, Novikov's principle does not resolve every paradox. Between 2020 and 2022, physicists Barak Shoshani, Jared Wogan, and Jacob Hauser demonstrated this with a striking thought experiment. Imagine you possess a working time machine and a set of balls that are either black or white. Whenever two balls collide, both change color. Black becomes white. White becomes black. Now, suppose a black ball travels back in time and collides with its past self. The collision turns both balls white, but the impact also deflects the time-traveling ball onto a trajectory that sends it through the time machine again. In this scenario, the exact same ball exits the exact same time machine at the exact same moment in the past, yet it appears to be two different colors at once. This contradiction cannot be resolved by self-consistency alone, but it can be resolved by parallel time streams. According to Shoshani, Wogan, and Hauser, backward time travel is only possible if the traveler emerges into a different branch of reality than the one they left. The black ball begins in timeline A, but exits the time machine into timeline B. In this alternate stream, it is the other ball, not the original, that later enters the time machine. The ball that emerges the first time and the ball that emerges the second time are no longer the same object, even if they share an identical history up to that point. The paradox dissolves, because identity itself has split. In this picture, time travel does not overwrite the past. It diverges. The universe does not collapse under contradiction. Instead, it branches quietly, endlessly creating new timelines where every logically consistent outcome can exist. And if that is true, then the price of time travel is not paradox. It is multiplication. Every journey to the past fractures reality, spawning new histories that unfold beyond our perception. The universe absorbs impossibility not by forbidding it, but by becoming larger than we ever imagined. And that realization brings us to a chilling conclusion. If time travel is possible, then the multiverse may not be a side effect of quantum mechanics. It may be the only way reality survives it. This kind of extreme mental gymnastics takes time to absorb. It pushes intuition to its limits and forces us to rethink what we mean by cause, effect, and identity. Yet, for all its strangeness, it offers a potential resolution to one of the most famous logical traps in physics, the grandfather paradox. If traveling into the past means entering a separate time stream, then the contradiction dissolves. You could kill the version of your grandfather that exists in that alternate branch, secure in the knowledge that the grandfather essential to your own existence remains alive in the timeline you departed. History is not overwritten, only diverted. In this framework, free will is restored. You are no longer trapped by a single predetermined chain of events. You are free to act, because your actions unfold in a new branch of reality. The many worlds interpretation can also be used to sidestep the bootstrap paradox. In the story of the time traveler, saved by an anonymous letter, the origin of that message seemed impossible to identify. No one appeared to write it. But perhaps the paradox only exists because we were missing key participants. Imagine this instead. A version of you in time stream A writes the letter and travels back to time stream B, where they give it to their younger self. That teenager follows the advice, studies physics, grows up, invents a time machine, and then travels back again, this time to time stream C, to deliver the same letter to yet another version of themselves. The letter appears authorless only because its author exists in a different branch of reality. The paradox vanishes, but only at the cost of invoking three separate versions of you, spread across three distinct timelines. If this feels like using a sledgehammer to crack a nut, you are not alone. The implications are staggering. The number of branching realities could be infinite. As physicist Bryce DeWitt once put it, every quantum transition taking place in every star, in every galaxy, in every remote corner of the universe, is splitting our local world on Earth into countless copies of itself. Not everyone was comfortable with this conclusion. John Wheeler, the physicist who coined the term wormhole, eventually abandoned his support for the many worlds interpretation. "I have reluctantly had to give up my support of that point of view," he said, "because I'm afraid it carries too great a load of metaphysical baggage." And yet, despite these reservations, the many worlds interpretation has steadily gained traction. Today, it has a growing and devoted following among physicists. In this view, reality is an ever-branching structure, an endless array of parallel histories, each one slightly different from the next, all unfolding along the vast, braided currents of the great river of time. As we move along our own world lines, sometimes faster, sometimes slower within the immense block universe, one conclusion is already unavoidable. Time travel to the future is not speculative. It is real. It has been demonstrated experimentally, and it happens continuously, woven quietly into the fabric of everyday life. Traveling backward through time remains far less certain, but on paper, at least, it appears possible provided we accept the deeply counterintuitive lessons of quantum mechanics and the possibility that reality is far larger, stranger, and more fragmented than our instincts suggest. For now, we must remain anchored to the present, carrying only memories of the past. Yet, we can take comfort in a remarkable thought. The past is not gone. It still exists, etched permanently into the structure of space-time, even if we can never return to it. And so we stand at the edge of understanding, caught between what we know, what we can prove, and what may forever remain just out of reach. You've been watching the entire history of the universe. If you enjoyed the journey, don't forget to like, subscribe, and leave a comment to share your thoughts. Thank you for watching, and until next time, the river of time continues to flow.